Hello, our project investigates a collaborative solution using shared control to bridge the gap between fragile autonomy and human intuition. Looking back at our initial goals, we achieved the main objectives of building a functional shared control system. However, some original goals were too broad, so we redefined our scope during the process. And instead of covering many shallow scenarios, we focused deeply on APF and static traps, ensuring the core arbitration logic is robust. Technically, the system runs on Mujogo with a unitary goto. It fuses inputs from a human and the AI, and our key innovation is the risk engine. It explicitly detects failures to drive the control sharing. And finally, the architecture. Data flows into our arbitration core, which calculates a real-time risk score. This drives the blending logic, dynamically adjusting control authority to maintain the optimal balance between human intent and AI safety.
The simulation presents the human controller. As you can see, the obstacles induce a virtual safety envelope. By that mean, when a forward component is given towards the obstacle, it's reduced to zero while the tangential component is still allowed.
The pure AI mode. The APF planner performs perfectly, efficiently guiding the robot straight to the target. However, complex geometry breaks it. In the U-shaped trap, the robot gets stuck in a local minimum, unable to escape on its own.
The simulation demonstrates a switch based arbitration between human and AI agents. When the human drives toward an obstacle, the AI takes over and navigates toward the goal. In this constrained environment with local minima, the robot becomes trapped near obstacle corners. Although control switches to the AI, the switch based arbitration framework does not include a mechanism to escape local minima, resulting in a stalled state.
In this scenario, we demo the system's baseline autonomy. The AI planner is navigating through the scattered obstacles using the artificial potential field. The arbitration doesn't disrupt the AI's performance when the navigation is smooth. Here on the left, human has a slight input. The dog followed, so we can say the operator can seamlessly intervene to adjust the pace if no immediate collision risk exists. This ensures human intent is respected with safety margins. In this scenario, the robot approaches a U-shaped obstacle. Currently, the system is fully autonomous and risk-free. Now, inside the trap, movement stalls, the system detects stagnation, and the predictive algorithm then confirms a trap, causing the risk to rise. Alpha for AI authority is reduced. The long yellow bar and the trap notice indicates humans should now take the main control. With no human input, the auto reverse reflex triggers, moving the robot backward to escape, but without human guidance, it remains stuck in a loop. Seeing this, the operator uses the joystick. The system instantly guarantees full control to the human for a quick rescue. Once the robot is clear of the trap, the operator releases the control. Since the risk is low again, the alpha bar returns to blue. The AI takes over and guides the robot to the final goal.
Looking at the results, Figure 3 demonstrates the switch based arbitration successfully preventing collisions by transferring control to the AI when human commands are unsafe. However, in Figure 4, in enclosed environments, the robot remains trapped in local minima, exposing the limitations of pure switching. This slide shows the behavior of the risk-aware blended arbitration. As risk and stagnation increase, the authority factor alpha smoothly shifts control toward the AI rather than abruptly switching. Unsafe human inputs are continuously suppressed in the final velocity command. Physical stall is reliably detected using force and velocity metrics, and when high risk persists over time, safety reflexes such as auto reverse and system lock are triggered. In summary, switch based arbitration is effective for immediate safety but struggles in local minima. The blended arbitration framework improves robustness by smoothly regulating control authority based on risk, enabling safer and more stable shared control behavior in challenging environments. The major contributions would be real time human AI shared control architecture, APF based AI policy adapted for shared control, risk aware arbitration using both switch and blending. Depending on the project's ambition and progress, these represent potential future improvements and extensions. Thank you. Now for the questions and answers.